Okay, so next speaker is Yang-Hui from London, Oxford, and Nankai on University at Bigdata.
Okay. Well, thank you very much for having me, and thanks to the organizers for this beautiful venue. And thanks for welcoming me to this community. Probably amongst you, I know the least amount of M theory, because I've really never worked on M theory, maybe except one paper. But that's really a quiver in disguise. So I'm going to continue in this vein on the machine learning topics of the session. And what I'm going to argue is actually slightly different from David's beautiful talk, is that string theory has actually provided us with a lot of labeled data. So let me begin with something. This is old school. This is really for the benefit of just for sanity more than anything else. We start with an equation of string theory which is indisputable. And then the story of 1984 of this, this is all story. And I'm very fond of V8. And this is why I begin the talk with heterotic string theory. That's where all this business really began. And the standard solution that these gentlemen had at that time was the Clabbiau solution, right? Ritchie-flat Kähler manifolds. In fact, at the time, I was told by Philip that at the time, these were known as Ritchie-flat Kähler manifolds. And it was actually the physicists who actually coined the term Clabbiau. So this is kind of an interesting historical note. The mathematicians did not call these things Clabbiau. So they called it in honor of Yao. But it is actually quite interesting that when these guys were thinking about this problem of string theory, of string compactification, or what we now call string phenomenology, mathematicians were actually following an entirely different program which led to the same, almost exactly the same kind of concern. And this is only more recently I began to appreciate more and more why they were thinking about this program. So let me just, what mathematicians were really thinking about is sort of a generalization of Riemann uniformization theorem. So which essentially says that in dimension 1, complex dimension 1, we have a trichotomy of Ritchie curvature. That it's negative, 0, or greater than 1. And in algebraic geometry, you will see a plot later of why this kind of trichotomy is so important. So of course, this goes back. We have index theorems, which this is all really well understood by classical results. But here's the plot in complex dimension 1, where you have sort of, well, here at least you have spherical geometry, Clabbiau geometry, and hyperbolic geometry. And in general, for algebraic varieties, you have Fano varieties and Clabbiau varieties, which is a sort of right in the intersection, and then varieties of general type. And the kind of classification, and at least even now, there are conjectures that the classifications of things of this type should be somewhat finite. And this classification should also be finite. By finite, I mean finite topological type. So here, in dimension 1, you see this very, very clearly. Right? And then of general type, you get infinite topological types. And it is still a conjecture of Yau's that indeed in each dimension, there is a finite number of possible topological invariants for Clabbiau manifolds. And this is a very nice thing. So in dimension 3, even though we have so many examples, if you just count the Hodge number, if you count the intersection number, if you count the second Chern class, we now have at least 10 to the 6th and rising every month of this number of possible vector as an integer vector. But Yau's conjecture is that possible number is still finite because of this general law in mathematics. Yeah.
Are these simply connected, the ones that you're talking about, the Ritchie-flat Kähler?
Yeah, sorry, yeah.
Sorry,
so,
but just
sorry.
So in G2, that's not the case, right? I mean, you have G2 holonomic manifolds with arbitrary B2.
That's right. Yeah, that's right.
So why is it though different? So it's not just Ritchie-flatness.
I think probably G2 goes into real algebraic geometry. I think you need the complex bit to make this kind of thing work. So anyway, the story goes that Strominger and Yao. So this is why Yao was thinking about this kind of problem and famously proved this, for which he got the Fields Medal. And the story was that they were actually neighbors at the IS in 1985, and this is why they were talking. This is the reason I believe sort of spiritually in string theory, because string theories always work on just the right mathematics at the right time, always, and sometimes ahead of them. This is just the way it is.
Is that all string theory?
Yeah, probably. Yeah, I'm sure.
Am I doing that?
I'm sure. By definition, by construction, we're always doing the right things. So anyway, sorry, this is supposed to be a 1. In dimension 1, the construction is very clear. It's an algebraic variety. So this is the standard cubic elliptic curve in CP2. In dimension 2, you have the quartic in CP3, and then you have this general theorem, of which the quintic is the special case. So immediately, this is immediately known back in 1985, that you get these 5 manifolds for free, and these are actually called cyclic manifolds. These are just different ways to partition integers. How many ways can you partition a positive integer into positive parts such that they sum up to one more than the ambient space, right? So 4 plus 1 is 5, and 5 minus, and then 4 plus 1 is 5, and 4 minus 1 is 3. You want three folds, right? Here, 3 plus 3 is 5 plus 1, and 5 minus 2 is 3, and so on. So immediately you have these 5. So these are the cyclic manifolds. You can show that H11 of this is just Z. So you can generalize this to complete intersection manifolds, which are just cases instead of taking a single projective ambient space, you take enough intersections, optimal intersections of hyperplanes of various degrees until you hit this, such that the dimension works out just right. So, and then this really became a big, so when these gentlemen were thinking about this problem, they did what we now call standard embedding in heterotic string theory, which is to take the commutant, you get a free E6 in this setup. And E6 freely incorporates the standard model, so that's why they were thinking about. Of course, we're much more sophisticated now. We can do much better phenomenology than that. But at the time, they were in this setup, the particle generations realized very naturally as the Hodge numbers. So this became the first challenge, the first challenge of physics to algebraic geometry, which is a very precise challenge. Can you give me any Ricci flat, compact, smooth Clavier manifold with Euler number plus minus 6? This is very precise. So at this point, Philip says, you go to take this problem and go to what's known as a card-carrying algebraic geometer. I'm not sure what card he's referring to, but I don't know, people carry cards. And Yao was certainly one such card-carrying algebraic geometer. So Strominger was next door. He carried him to this problem. And then Yao immediately checked on the quintic, and this just didn't work. You can show that the quintic is minus 200, and minus 200 is very far from plus minus 6, because that's, in this setup at least, this would give 100 generations of fundamental particles, which is not that exciting for physicists. So, fine. Why stop there? So there is an entire program. So this sort of business really proceeded in 4-year plans within the late 80s to the early 2000s in terms of mapping out the landscape of Clavier constructions. So the first one is what these guys did for the first 4 years, and they were called sissies because they just generalize the quintic in CP4. So if you just look at some examples, instead of taking a single CPn, you take a product of P and 1 all the way up to P and M, where each of these are multi-degrees of the hypersurfaces, one slice at a time. So of course, they're simple combinatorial constraints. Each row sum must be one more than this, and so that's the vanishing condition, right? And the sum of these numbers must be 3 more than the number of possible columns. So for example, the quintic would just now be written as a 1-by-1 matrix, the number 5. There are other ones like, take your favorite, the doubly elliptically fibered Schirm manifold. You can write it as 1, 3. You can just do combinatorics, right? And these kind of things became central to phenomenology within the first decade. And so the people like Distler and Green and Ross were really working on this, mapping this out. And then this was done very quickly. People realized, these guys realized, that we need to classify these matrices. Right? And they very quickly realized that classifying this by hand was out of the question. And in fact, even on the computing technology at the time, this was also out of the question. So they immediately employed the best computer they had on the planet at the time, which was the CERN supercomputer. And they put this constraints, and they started, these are dot matrix printouts on the supercomputer. If you wish, very little of the original data, talking about data preservation of even this error is retained. There's one hard copy version of this in Philip's office. It's about this much. It's 7,890 pages of printout. Each one is one dot printout of one of these matrices. Anti-Lucan has a magnetic tape version of this. But luckily, we have resurrected this, and now it's freely online. So if you're bored, please go look at this data set. So this is a data set about 8,266 distinct Hodge pairs and 70 distinct Euler numbers, which is kind of nice. By late 80s standards, this is very large data. But it was also that this is biased data. All of the Euler numbers there are negative. So if you didn't know about mirror symmetry, you would have conjectured that all Clavier manifolds had negative Euler number. So this is very dangerous to do big data, right? So this is a perfect example of biased data that you wouldn't even know that it's biased. But luckily, mirror symmetry was known right around about this time, so they knew that this was a biased set before making any conjectures. So in order to unbias this, they tried something else, which is to weight CP4 into weighted CP4 and consider hypersurfaces in that. And again, this was classifying, it's just inequivalent 5 vectors, and around about 8,000 there. And now you get around about 3,000 Hodge pairs, and now you have a much more balanced distribution of Euler number. Of course, the most hardcore of this 2 decades of endeavor was done by Kreutzer, the late Max Kreutzer and Skarka, where they used a theorem of Batirev and Borisov, which states that if you take a polytope, an integer polytope, if it is reflexive, so in other words, if it has a single interior point, and that all of the faces are distance 1 from this, then you have to just consider such polytopes. Construct the toric variety from this, and take the anti-canonical divisor within this toric variety, it's guaranteed to be Clavier. This is a very nice and beautiful construction. Their mirror symmetry is just a symmetry of the polytope. So the question became, how do you actually classify these polytopes? I'll show you in a minute. So this is one of my favorite things ever. So in dimension 2, this is known to Fano and Del Pezzo, back in the late 19th century. You can just check up to SL2Z. These 16 are the only ways you can draw integer polygons such that all of the faces are distance 1 from a single point. So this is 16. And already at dimension 3, the result is unknown. So in dimension 3, how many ways can you write? This is a problem you can explain to a high school student. And yet this is an open problem since Fano, until Kreutzer and Skarka did it by brute force and classified it in dimension 3. And you can make models out of these. And the number is 4,319. And so these will give very special K3 surfaces. These give very special 16 elliptic curves. If you want, but the one they wanted at the time was 1 dimension up. So that was really the tour de force of Kreutzer and Skarka. And they ran it for 6 months continuously on a dual Pentium SGI machine, all of which are now completely obsolete technology. But it's quite impressive they did this within the late 90s. So they came up with this beautiful number, 473 million, and 30,000 distinct Hodge numbers, and then a distribution within 960, there. I'll show you some plots in a minute, but what's interesting is it is still an open problem what the next number is. No one knows at all. I've asked combinatorists, graph theorists, people who spend their entire lives on this. They don't even have an idea of a generating function for the next number. And I think you were suggesting, right, last night, why didn't you look at on OEIS, what the next number might be? But the entry on OEIS were put in by this gentleman, so it's not too helpful. But Shkaka did this really beautiful stuff on the hardcore computation just last summer, and the next number is at least this. But we have no idea what it is. It will be very beautiful to, I mean, this is a high school problem that requires a problem, but it's an open problem in combinatorics. So we have no idea what the next number is. So at least this number will give you a very nice landscape of Clavier fourfolds. So I'll show you this all the time now. I ripped this off the internet. This data science revolution in string theories are actually much earlier than you think. So these guys have been working on it for 20 years. And apparently, for experimental physicists, data science, this whole machine learning business is even earlier. So here's a plot of the Hodge distribution well, amongst the various constructions of the compact Clavier landscape, where I shamelessly advertise my book. At some point it will appear. You can read about it. The largest one that we know is the Kurzgesagt. And so here is the Hodge pair plot of the 30,000 Hodge numbers. And you will find a black and white version of this plot in Philip's office, framed. My contribution to this plot is inspired by my 4-year-old daughter, who is very good at coloring things in. So I colored this in. This is the log density heat plot of the multiplicity per Hodge pair. So you can see there's much more focus somewhere over here. In fact, if somebody runs you on the street and asks you, what is the most typical Clavier manifold? Your answer should be, it's 27,27. It is by far dominating. We have no idea why. There is something like 1.5 million of these that are 27,27. 27 is a good number. It's 3 cubed. 3 is the trinity. I don't know.
Is it even apparent why you get a smooth answer for the distribution?
Pardon?
Is it obvious why you'd even get what appears to be a smooth distribution?
Oh, I think it's a bit deceptive. We don't even know what to do. I mean, this is just Mathematica's extrapolation. So you see a lot of the whites are blanks.
There?
Nothing that from the Kurzgesagt list.
Okay.
This could be more populated. So actually, what is interesting are these. We have no idea why this area is why. So this bound is just the shift of coordinates. This is Euler number plotted versus H1 correspondence number, and then mirror symmetry is left-right mirror symmetry, which is nice. And we have no idea why this is true. So Waddy Taylor's been doing a lot of work explaining that, showing, in fact, I think all of these are elliptically fibered. But we have why there's none here, we don't know.
But I just mean that there's obviously quite a lot around 2727, you say, but then there's quite a few at like 2726 or just nearby, whereas you might have thought that.
Let me check.
Okay.
Yeah, that's a good question. I'll have to check on that. And also 960 plus minus 960 is the largest. It hasn't been broken. This record has not been broken in 40 years. No one has ever found a Clavier, a smooth compact, a simply connected Clavier, whose Euler number is bigger than 960 in magnitude. Which goes very well with Yau's conjecture that there's a finite number of possible such things. But 960 is a very beautiful number. It's twice 480.
Just to be picky, correct me if I'm wrong, this is all for toric hypersurfaces?
This is for toric hypersurface.
For example, there are lots and lots of other constructions of Claviers. There's Pfaffians, intersections,
That's right.
Riemannians,
That's right.
all that sort of stuff, and this doesn't even get into any of those.
That's right. Oh, sorry? Oh, sorry, yeah. Yeah, it would be nice to superimpose that. But what's interesting is that if you do the double hypersurface in toric 5, it doesn't break this shape either. So I know James and Lara have a lot of Grassmannian data, but I haven't seen a plot over this, but I think this vague shape hasn't really been broken. And 960 has also not been broken ever. Just kind of curious.
Does it have to be connected? Can we find something far away? Or
This
Or
is
it's
all
not
that there
interesting.
is within this 473 million.
I see. But
So
could we?
lots of stuff to look at, even in this. So people are still data mining. So it's, notably, the group in Northeastern, like Brad Nelson and Jim Halverson, a lot is still data mining. One thing I should emphasize is that this is just the polytope. It's 473 polytopes. Each one of them requires triangulation before you can even construct a, you need resolution. So the actual number of Claviers is much, much, much bigger than this. The Hodge numbers will be uniquely determined by the polytope data, but the intersection numbers and the churn classes will require the actual triangulation. So we've actually set up a database where we triangulate just one by one, and we got up to around about H1 equal to 7, and that broke the best computing resources which we had at the time. We were proud we had a Microsoft grant to do this. And then there was we only got up to 7, but in 960 left to go. It is what it is. So here's a bit of speculation. Well, I don't know. I mean, I always look at selecting them within this landscape of, whatever, Claviers and certainly all of the other geometries to be very much like the exoplanet search. Right? Which universe is favorable to ours? I don't know. So just briefly on some more recent progress, it is possible to find exact MSSM content. So in the sense that if you so now we're more sophisticated. You take the Clavier, you take a stable Hermitian vector bundle, and then you can get SO10 or SU5, and then you can use Wilson lines to break into exactly standard model, et cetera, et cetera. So a lot of progress has been made, and it's reached culminating in this beautiful paper of Lara, James, Andre, Bird, and Aaron, where they scanned through a lot of these, and they found about 200 within 10 to the 10 that are exact MSSM spectrum. So it's kind of nice. I mean, this is 1 in a billion. It's roughly, that's an old paper of Dieter Lust in type 2A, which says 1 in a billion, and this is about 1 in a billion in heterotic as well, just to get spectrum.
But, sorry, when you say the spectrum, you mean of the chiral matter?
Of the chiral
There's
matter.
all sorts of non-chiral exotics.
Oh,
You have
no,
idea.
sorry. No, by this I mean, so all of the anti-generations are gone. I mean, you really want exact MSSM matter content and nothing else. No,
And nothing else?
Nothing else. And that was part of the challenge. So the first ones were found in the Penn collaboration. We were lucky to have found one, but then these guys made an industry out of it and scanned through this many bundles and found 200 of them had this exact no field theory massage needed kind of solution, which is kind of nice, but 1 in a billion. But even there, you estimate even within, this is just within the CISI data list. If you go further, you still expect a lot of exact MSSMs. Right? I think Philip is still of the philosophy that our world is very, very special. So. That's exactly what Tristan Hoopsch said when we had the paper out. He said, you should have called it a mole of standard models. But the idea is you do cut the landscape down a lot, even if you put mild constraints like particle content. But because the landscape is so large, even within the tiny corner of Clavier compactification, you could still end up with very large numbers like this. And of course, this whole program really was put on hold in the mid-90s because of all of this explosion. Right, so I need not say further. You guys are much more expert on this stuff. Of course, I've mentioned I come from the school of Hanani, that even in the non-compact case, there you have sort of a translation between quiver data and the gauge theory data as well. So you have a translation in that context. Right, so all this is standard stuff. So now I tell, I don't know, in more populist propaganda, where I'm asked to defend string theory from time to time, And I said, well, because of this landscape, this vacuum degeneracy problem, we should look at it under positive light, because it translates a very hard problem, the quantization gravity, to another very hard problem of statistically looking for the right geometry. And I think in many ways, this is a richer, much more interesting problem because it involves so many different branches of mathematics and physics, at least. But to this crowd, I don't need to do such populist propaganda. So just to summarize, over the last 20 years or so, not just the string community, but the mathematics community has been very active in compiling data. And a lot of this data has actually been motivated by string theories. Just to give a few examples. So there's the SAGE project. This is sort of the umbrella project for all of these things, which is a Python-based project which tries to compile as much stuff out there as possible. So for example, GAP, not your genes, but it stands for, it's a horrible name because if you try to Google GAP to get to the homepage of GAP, the first 20 hits are genes. But GAP stands for Groups, Algorithms, and Programming, has about 10 to the 7th finite, so it has all finite groups up to order something like 2040 something. And that's about 10 million groups. You have everything you ever want to know about these are there. So just give an example. There are things like GRDB, the graded ring database, which maintains all of the finitely generated graded rings that you can put on a computer. So there's about on the order of less than a terabyte of data of pretty much all known varieties that you can at least write down. So that's kind of a good thing. There's the Cremona database of about 10 million elliptic curves, which is good. And of course, the Kreuzerschake database and our various minings of these databases. So these are all free. This is great. The great thing about this community is we're not Wolfram. We make this free, and you can download them. They're on the order of gigabytes. So for example, the entire Kreuzerschake database is nothing but integer polytopes, just vertices of the polyhedra, and that's about 6 gigabytes. Fits very comfortably into a USB, and you can take it home. And if you're bored at night, just look at them. But this extended community has been using various software like Singular, Macaulay, and you name it, just to try to study various properties of this. And the archetypical problems very often reduces to integer tensor manipulation, because I gave you an idea of the sissies. There is just some matrix. That's your manifold is just literally this integer matrix. Or if you're looking at the toric variety, it's just literally some n by 5 entry of polytope vertex data, and so on and so forth. And then you just use whatever technology you have, from algebraic geometry to whatever, to finite group theory, to try to compute the right things that you want. Right? So the good thing is that these are free, as I said. The bad thing is the generic computation in algebraic geometry is very difficult. It's provably so. So basically, any computation in computational algebraic geometry reduces to step number one you want to do is to put your polynomials into some Grosvenor basis. So this is the polynomial generalization of Gaussian elimination. So that's the first thing you want to do. Gaussian elimination is n log n, so it's not too bad. But a polynomial reduction, in the sense, is double exponential. So in principle, I can put 473 million Clavier manifolds onto Sage and just hit run and go have coffee. But each computation is double exponential. If it's just Gaussian elimination, I could just wait, maybe 10 years, and I can scan through that entire thing. But unfortunately, I was going to be bold and show you a Sage computation on one of the manifolds, but I think it's going to crash. Even on something slightly more complicated than like a two hypersurfaces in CP2 cross CP2 P1, your computer begins to choke precisely because of this bottleneck. So that's the bad thing. So even though we have all of this data, we can't just brute force it. And okay. So that's how we stood until recently. So, well, there's the good and the bad and the whatever, whether you could actually borrow ideas from big data. We now actually have properly big data. So, as I said, the typical problem in string theory and also in algebraic geometry is some kind of integer tensor output in some kind of integer. Integer because you're dealing with topological invariants, like H11, H21, or because they're generations of particles, and so on. Is it possible to machine learn this? So that's a speculation that I had back in 2017. And because actually there's a quick succession of papers in 2017. We were all friends, but we were all doing this independently. This is kind of nice. I can't resist this, since this is a string crowd. You can see the series of annual conferences that have started in string theory. Right? 86 was the first strings. 2002, first string Pheno. And I mean, a series. And then there was the NSF string vacuum project that Keith Dinnis was responsible for mainly. And this first string math was 2011. 2014, so this is probably my only contribution to string theory. I made sure there's a string session in SIAM. You guys probably don't even know what SIAM is. It's the Society for Industrial and Applied Mathematics. So this is huge. 600 people come to this, or more, probably more, every year. They have annual conferences. So that the string theory has a foothold in that. You're trying to argue, talk about impact. I don't know. So far, I haven't got nothing out of this, other than just making lots of new friends. But in 2017, now there's the first string data, and this is an ongoing annual conference. So this is kind of nice that you can see a glimpse of what the progress in string theory has been since the beginning. So here, since David gave such a beautiful talk, introduction to machine learning, I'll be very brief. So I very quickly changed this slide to supervised machine learning in 1 minute, okay, as opposed to 5 minutes. So the reason I was thinking about this problem back in 2017 was just because, if I gave you these digits and ask you how does the computer recognize this? So for mathematical physicists, our natural tendency when given this data is probably to set up a Morse function, to see the critical points. And this is a good analogy, because computing Morse functions is difficult. And this kind of feels like what we have been doing in terms of computing cohomology. And that's exactly what Google does not do. Right? It doesn't do something that's expensive. What Google does is just, as David points out, it just machine learns. There's a database. You can take the NIST database of this. These are labeled. I think some poor person or persons actually labeled them one by one. But given enough years and people, you will label this. This reminds me back in the day when I was in a class with Dan Friedman doing SUSY. Dan Friedman says, this is a perfect problem adapted for very large parallel clusters of graduate students. So this is, I assume NIST has gotten this because of this kind of abuse. Right, so just very, very briefly, Dave has already told you about this, but just want to emphasize that supervised machine learning is just glorified nonlinear regression in a very, very glorified way. But I just want to emphasize this really started in 1957. This is before even the personal computer took form. And the single neuron was called the perceptron. The idea that the fact that it ends in TRON shows that it comes from the 60s. We would never call something the perceptron now, because it's just so outdated linguistically. So we have some cost function, you minimize it, and one thing I just want to emphasize that what you do, what machine learning people do is to take this multi-noded lists of neurons. But each neuron is essentially some nonlinear regression, some activation function. And then the magic of neural networks is in here. It's sufficiently complicated that there are enough nonlinearities that it should mimic the brain in some sense. One of the key things you want to do is what's called cross-validation, which is you got to make sure, because these are labeled data, you got to make sure when you train on a data set, you validate on something you've not seen before. Otherwise, you could just be overlearning by overfitting. There's so many parameters. You could do anything. The universal approximation theorem says you can approximate any function. Then you can just simply tune it. So this is why it's important to do cross validation to make sure you train on the subset, and then validate on the one that you've not seen before. So let's just apply to this. So as I said, the neural network doesn't know what algebraic geometry is, just like the neural network does not know what these things are. I mean, to us, these are numbers. Right? But this computation, from this to this, is done. In fact, Hubsch's very nice book is an entire book dedicated on showing how to do this computation. So here, if you just read it, this is 1, 2, 3, 4, 5, 6, 7, 8. That's 8 polynomials in P1 cross P1 cross P1 cross P1 cross P1 cross P2 cross P2 cross P2. So however number of variables they are. And you just write them out in principle. I mean, in principle, you could take that, feed into Sage, and hit return. And I promise you it will blow up because the Grosvenor basis computation is double exponential. Nevertheless, these gentlemen, they didn't have Sage at the time, so they really bit the bullet of actually doing this computation. So, if you want to do it properly, even on the quintic, just for example, we know what to do. You chase sequences until you're blue in the face. You set up the early sequence from the ambient space, and you induce from this short exact sequence to this long exact sequence in homology, and then you try to hope to God there are enough zeros in the sequence, and then. Right. This is actually my secret main motivation for getting into machine learning, because I've been doing this computation all my life. I can't take it anymore. Right? Even with the help of computers, because it's really hard. And then even when God helps you and there are enough zeros, and sometimes you're still stuck with a co-boundary map somewhere. Sometimes Laura can stare at one of these co-boundary maps and say, okay, well that's rank 1 or something. But this is hardcore. This is too hardcore. Right? But nevertheless, because of books of Hubsch and so on, this computation has been done exactly like the way graduate students have been recruited to label the NIST database. So once it's labeled, it's great. And then as far as a neural network is concerned, this long exact sequencing cohomology is just this association rule. Right. This is the pixel representation of this as an image. So as far as a manifold is concerned, it's just this picture. And then you've got 8,000 of these, right, plus all permutations. So you can instantly get 100,000 labeled data. And then you cross-validate. At the time, you could have gotten anything. You could have gotten absolute nonsense. But strangely, I didn't get nonsense. At the time, I wasn't sophisticated enough, so I just tried a very quick estimate. So if you want to know H11 is bigger than 5, less than 5 as a binary classification, feed this. And he got to like 99% within 2 seconds. I said, wow, holy crap, why do cohomology anymore? Right? But okay, I'm cheating because some people have done the hard work for us, or including ourselves have done the hard work for us. And then you can do much more sophisticated stuff. So my master's student, Kieran Bo, especially in this series of projects, Kieran is my master's student in Oxford, and this guy eats 20,000 lines of Python for breakfast. So I was doing it on Mathematica because we physicists are Mathematica people. And I'm now, transitioning into Python, but into TensorFlow, which is the proper way to do it. And even so, H11 in the CISI data list go from 0 to 19. So this is a 20-way classifier of pictures, just classifiers on pictures. And you could very quickly get to 90%, over 90% precision using, I think, a neural classifier. So that's nice. Let's do more interesting things. I mean, obviously, one of the things you want to do is, for example, it was just, at this point, I was like, oh, wow, this is like a hammer let me just start smashing every single problem I can think about on God's green earth. And now, so at this point, I'm going to entice you with various interesting problems. How about distinguishing elliptic fibrations? So they're very sophisticated theorems and conjectures of algebraic geometers, just looking at a manifold to see whether it's elliptically fibered or not. Right? You can check it. There, what you really have to do is to find a basis in H1, check the triple intersection for all of these curves, and see, et cetera, et cetera, et cetera. But luckily for the CISI data list, Sunju Lee and the Virginia group have actually classified this, trained that to this data, and then by even looking at 40% of the data and then cross-validating against remaining 60%, so it's only seeing 40% of your data, it's learned what elliptic fibration means. Learned in the sense that we have no idea what it's doing analytically, but it's extrapolated some pattern that we have yet to understand. So I'll talk more about that in a minute. But nevertheless, you're getting almost 100% accuracy. It's almost completely good in this. But the idea is that this computation takes less than a minute on a laptop as opposed to using supercomputers for months. Why? Because it's guessing, but it's guessing right. So Fabio Rulla did more sophisticated stuff with bundle cohomology, right? So we were just talking about Hodge numbers, and there you also get very good results. There's an interesting paper of Calum, André, and André, which is actually, what they did, this is actually kind of interesting. So computing the cohomology of a line bundle in an algebraic variety is extremely difficult. So for projective space, the bundle cohomology is just Kunith, some fancy version of Kunith. But even if you take a single hypersurface and try to compute a line bundle on that, the formula is so out of control. Just take this simple example, O of K1, K2 over not P2 cross P2. There, Kunith would just help us. But over a hypersurface in P2 cross P2, it's not known. Until this kind of results, where they actually just started plotting, use chase sequences, and they were able to exactly pinpoint the regions in K2, K1, K2 space, and got 100% accuracy. And then they started to conjecture what that formula might be. And the formula, as you might expect, is some kind of a sophisticated decision tree. There's no analytic result. We know the index is analytic because of the index theorem, but each individual piece in cohomology is very, very difficult. So it'll come to things like, if K1 is bigger than K2 squared minus the K1 choose K2, then the answer is 1. If K1 is between this and this, the answer is 2. But then what the machine in that paper is doing is actually picking out what those boundaries are. And then you go back and you can actually prove exactly that it is what it is. So the machine is very good at doing this kind of computation. So why stop there? Of course, Clavier metrics are great. Right? So Donaldson gave a very efficient numerical algorithm to find Ricci flat Kähler metrics on compact claviers. Machine learn that. Right? My life now, everything is like machine learn it. Especially looking at my daughter and my infant son, it's like that's what they're doing. They're machine learning life, and just by extrapolating on the tiny fraction of the known Donaldson result, you can actually get very exact Ricci flat Kähler metrics on Clavier manifolds, sometimes 100 times faster than the Donaldson algorithm. And we have absolutely no idea why. It's just doing some regression, it's extrapolating. So it does actually help in the long run, this kind of idea. So, which got me thinking why algebraic geometry over C is so good to machine learning. And I will give examples of what's bad shortly. Because the core computations, as I said, is finding Grobner bases, whatever. But all of these computations, at some level, reduce to integers, finding integer co-kernels or kernels of matrices. And that's exactly something that neural networks are good at. So why stop at geometry? Why not try larger and larger classes of problems in mathematics? So this is a paper with Min-Young Kim, who's a number theorist, which on a sequence of quite interesting questions. Given a Latin square, a Sudoku solution, can you train a neural network to recognize when a Sudoku is actually the Cayley multiplication table of a finite group? Because GAP has 10 to the 7th number of finite group data, we can extrapolate some of that. And this one was actually very good. You can see that it kind of learns this rule. And a much more sophisticated one, I can talk more about this later, this is a much more interesting one, is can you recognize just by looking at a Cayley table whether this is the multiplication table of a finite simple group as opposed to non-simple group? And you could see that at 10%, it's already getting 95% of such answers correct. Right? This is interesting because we use the support vector machine here. And one of the reasons I like support vector machines, so basically this is something that takes your data and tries to find optimal hyperplanes that separates yes or no answers. So it is possible that if you plot finite groups in the space of all groups, there is some kind of hypersurface that separates the simple from the non-simple. And that would be a very remarkable conjecture to make. So we have, well, I can tell you the equation of this hypersurface, but it's kind of complicated and I haven't gotten much intuition about it yet. But this would be a very interesting approach to finite group theory. So more recently, why stop there, right? I played with card-carrying data scientists on Birch, Swinnerton, Dyer. Now you may ask why I chose BSD. It's because BSD, well, obviously it's a hard and great problem in number theory, but it's the most analytic of all the number theory problems. Why don't I do Riemann hypothesis? Why don't I machine learn the Riemann zeta zeros? There, because the dimension is low, I mean, there's not much to do. There's the zeta function, and then you just try to see whether something falls on a line. I think that's not enough stuff to look at. Whereas BSD is much more precise. I won't get into the details, but there are 7 exact quantities, all of which are extremely difficult to compute. The weak version of the BSD conjecture is that, for some elliptic curve, as the L function, the pole of the L function is the rank. The order of the pole is the rank, but the strong BSD conjecture says that you can actually tell what the residue is, the leading coefficient is, and it's given in terms of this. So why not use some decision tree to see if you can extrapolate these complicated quantities? Luckily, Cremona has the database of 10 to the 7th, 10 million elliptic curves, so we downloaded that, trained machine to see whether we can, and these things are actually, so the Sharferevich group and the period are actually very good in terms of recognition with this. So okay, so good. You can see where I'm getting at. I'm trying to set up a hierarchy of problems which are good and respond well to machine learning and which are not. Right? So I've sort of gone beyond string theory. And so obviously I tried this one because I need to break a bank at some point. So here's an interesting machine learning, supervised machine learning problem. Feed in the sequence, 2 goes to 3, 2, 3 goes to 5, 2, 3, 5 goes to 7, so on. And then feed in somewhere in the thousands, try to predict the next prime. Or if you wish, let's have a different representation. How about a fixed window of, say, size 10 of yes, no in terms of prime or not, and the next one is labeled to be prime or not. Train that to 100,000, and then try to predict what the 10 millionth one might be. So far, I have not been able to break any bank, which is actually reassuring. Not so reassuring on my bank account, but I'm very assured by this fact that the machine could not do any better than 50% random guess on this one. Because primes are primes. You can't, it would be crazy if some gradient descent algorithm could start predicting any pattern in this. So now let's do something totally crazy. Why stop even at the mathematics? So this is a paper which I really enjoyed working on, which is this is very much like a Boltzmann machine that David was talking about. So there is this thing called WordVec, where you take a document and you essentially set up a context window as you run through the document and set up this partition function and extremize this. This is a very simple feed-forward neural network. And then you're just trying to find so what you end up doing is to take any document, you optimize the word distance between words. And then it'll produce the optimal vector space where each word in your document is mapped to a vector, an optimized vector. So this algorithm was done by Mikolov, who was then immediately hired by Google and made tons of money. But this algorithm is great for us because we then applied this word2vec to all of the titles of archive. This is interesting. Unfortunately, I couldn't convince Vishnu and Brent to drop everything they were doing, because at the time I dropped almost everything I was doing. And I'll show you why in a minute, because there's some fundamental importance to this problem. We could only get titles because, well, obviously we want to do full text analysis and text full abstract, but I think Ginspark is going to ban us if we start auto-downloading too much. But just to give you a flavor of the 1 million titles, within the word frequency, so this is basic word frequency analysis of the archive, you can't really tell too much difference between HepTH and HepPH, right? The word model is predominant here in these three sections of the archive. The next one is probably black hole for HepTH, interestingly. String theory is up there. Dark matter for HepPH. Lattice, this is lattice QCD. HepLat, and then this is GRQC. Black hole is the most prominent word. But you can't really distinguish them. This is just frequency analysis. The point of word2vec is that it does something much more sophisticated. It gives you the vector that all of these words map to. And here's something that's very cool. You can get what I call linear syntactical identities. Having seen all of the titles on the archive, historically, it has learned that the word bosonic plus, because they're vectors, I'm doing vector addition, plus string theory gives the word open string. It has learned that holography plus quantum plus string plus ADS is extremal black hole. This is purely by context match, right? It has no idea what it's doing syntactically or semantically. It's just doing syntactical matching. And I love this one, string theory plus Calabi-Yau is M3 plus G2. This is fantastic. Of course, I'm cheating here because I've not given you examples of where it gave absolute nonsense. Because it doesn't know what it's doing, but at least this one's really struck me. Right? This is totally cool. I mean, it's just really looked at 1 million titles and has extrapolated information of this type, which is kind of cool. And you can do much more than this. Of course, you can do archive classification. Just by looking at the title, can you tell which section of the archive you should belong to? And indeed, you can tell to grade the correlation function matrix. Of course, it's not extremely good because we're just looking at titles. If you put in abstract, you expect to do something much more. And then this is the coolest bit, right? Then you check against Vixra, right? Right? So in other words, what we wanted to test, and the hypothesis is, are crackpots syntactically even self-consistent, right? And the answer is no. So within Vixra, you can't really distinguish between their HEP and they have a QGST version. Really HEP and Q. This is quantum gravity and string theory. You can't really differentiate between these two. Whereas here, HepTH really is different from GRQC. This is the correlation matrix. You want to be as diagonal as possible. And then we check against Times of India. Why? Because you can't download the Times. But very graciously, Times India allows you to download its all titles from its history. There you can check that it is very different from if you set up the full cross-validation using a support vector machine on top of the word vec. This classification actually tells you, yes, this is kind of different. But the most reassuring thing for me in this exercise is that indeed crackpottery is crackpottery, which is good. And that we have a consistent syntax that the archive as a scientific endeavor has at least a consistent syntax, which is kind of nice. But this is no joke. In July last year, these guys had this very influential paper in Nature where they did exactly the same thing. They took 3.3 million abstracts, so they did a much, much better thing, using exactly word2vec, the same kind of analysis. They downloaded the entire corpus of what is known as the subject of material science, right, essentially. And they learned new structures of the periodic table, and they predicted many new thermoelectric materials just by looking at things. So they were starting to tell, go and measure this. This is going to be better than whatever you've been doing. And this is true again and again and again. So what I was hoping at the time was to predict the next revolution in string theory. Unfortunately, I couldn't do it because we were just looking at titles. But I don't think it is entirely a joke to think that such an endeavor is not impossible. Again, I needed much bigger clusters of graduate students. So in other words, when you think about questions like, is a topside paper syntactically different from a non-topside one? It is entirely possible. So you want to do cluster analysis of all of the greatest papers in the history of the field and to see whether they have syntax which is different from non-influential papers. This is obviously something to do, but well, I need clusters of graduate students for this. So I'm probably running out of time. So from back to this string landscape problem. So for physics, my motivation is really twofold. In the physics, I've given you an idea that we have way too much string landscape. So brute force scan search is not possible. It's just out of the question. So the statistical approach to the landscape is really the way to go. But also on a more, I call it fundamental or call it extremist point of view, I'm really interested in what is the hierarchy of problems that are dealable by neural networks or generally techniques in machine learning. So, so far experiments have shown that numerical analysis is good. Algebraic geometry is a bit harder. So this means the rough prediction accuracy is slightly worse. So combinatorics is a bit worse than algebraic geometry. And of course, the hardest subject to learn is number theory, as you would expect, especially anything that has anything to do with primes. And here is essentially the machine. I could not find an algorithm. I tried every single neural network. I tried to tune every hyperparameter that I could, and I couldn't do anything in this, except maybe BSD. But maybe with a Boltzmann machine, I can do better. I don't know. Maybe if I can get rid of this hyperparameter tuning, maybe I can do better. I don't know. My friend Boris, who is a professor of logic, very appropriately said, what you're doing is syntax without semantics. At some level, it is true. Supervised machine learning is that, because you can't write down analytic results. But on the other hand, it's really, the kind of experiments that we've been doing here is really sort of the AlphaGo level. We want to go to the AlphaZero level. And at some point, this is really the Vygotsky stream of completely automated theorem proving. So, and this is also not a joke, because in November, just 2 months ago, this paper appeared in Nature, where these gentlemen created a neural network, which is an autoencoder, where they fed in some basic information, like harmonic oscillator, some Newton's laws, and they were able to extrapolate from that, so just by looking at the relative motion of Mars to Earth, they were able to, this autoencoder was able to return the fact that, it is probably much more probable that the Earth is not the center of the solar system, without any further input, that indeed there should be some other body that is the center. At least that is the claim of their paper. So what I'm hoping in this kind of experiments in mathematics is to go, this is sort of the AlphaZero level of where we want to go with this kind of exploration. So I think I'll stop here. Thank you.
Thanks. We still have time for a question.
So Sophia has to do with the string data conference?
Well, Sophia came in 2017, and Saudi Arabia immediately made Sophia a citizen. I think UAE should also make Sophia a citizen. And it just so happens the first data, it's 2017, this kind of stuff was in the air.
So it seems like this goes beyond string theory, right? You initially wanted to use this for Calabi-Yau moduli spaces,
Right.
moduli space of Calabi-Yau spaces.
Right.
But now you're venturing.
Exactly. I
in
just
other-
want to venture on every. I feel like a kid in a candy store, just because there's so many problems out there, and I just want to see how they respond to this kind of very simple neural networks, which is actually quite different from what some of my friends are doing, which is they want to say, for example, they want to machine learn bundle cohomology. What they're doing is to create an architecture which has built in the symmetries that are likely to generate this computation. Or find, for example, if you're looking for, say, computing line bundle cohomology, you would like to build some cubic activation functions because of the triple intersection form and so on and so forth. There you can try to home in, and you can get pretty precise conjectures that way. But I'm taking more of the candy store approach, which is if you didn't know how cohomology worked, could you find simple? Because of course, if you take very complicated neural networks, you can approximate anything. Can you find very simple networks that could finish things in a matter of seconds to try to guess new approaches to problems, whether it's in string theory or algebraic geometry or number theory or combinatorics, that could guess at better solutions? Some of these problems, like traveling salesman, which we know is a great problem, people have been doing machine learning on this. Of course, you're not solving the traveling salesman problem. You're just sort of stochastically solving it in the sense, sure, I can't give you an algorithm better than brute force to solve the traveling salesman, but I can give you a neural network which, 90% of the time gives you the right answer. And that's sort of bypassing the hard theorems in complexity. So I'm hoping at least this kind of approach would generate potentially new ideas in approaching problems in mathematics.
Sure.
So for example, the finite groups one would be a good one.
Thank you.
I'm trying to think how to phrase this question. You have a very biased data set where you tell us all the things that really worked, maybe one example where it didn't. But do you have a feeling of a more technical thing of the problems that machine learning are good at and those that it doesn't? So you get the example of primes where it doesn't work. Is there some way of understanding the type of data sets where machine learning is amenable or not?
That's a very, very good question. This is what I actually want to understand. That's why I'm doing this experiment.
Yeah.
I think, this may be too bold a claim, that almost all problems in algebraic geometry over C are good. Because pretty much any computation in algebraic geometry is about finding sequences of integer matrices where you have found kernels and co-kernels. And that the machine is very good at doing. More sophisticated things.
I think that mine was a sort of general thing, and then maybe a comment. I mean, when I said about the bias set, I mean, and I've been to all these conferences like you, and everyone reports all of the things that works. And I wish there was a website that reported all the ones that didn't work. So then we'd have a chance of trying to find a pattern within the machine learning problems that work and those that don't.
I've been keeping a tab of, that's what I want to, that's exactly the point of this. I want to keep a tab of all of the problems in increasing, but I mean, there's a measure. You just have to take, root mean squared of the error, or you take, whatever R squared coefficient or Matthews coefficient, just to list out all the problems which I'm trying to set up this list, and it should be put out there in some GitHub or something. So for example, I try something like here's a good one, like looking at a graph, a finite graph. Just look at its adjacency matrix and predict whether this graph has an Euler cycle or it has a Hamilton cycle. The Euler one is much, much better than the Hamilton. Sorry, other way around, for some reason. And I couldn't break it using any other. So there's a percentage you can. But the worst of them all is primes. And you would think it's such a simple problem because I literally have a 10 vector or 100 vector of ones and zeros going to 1 or 0. And you just feed in 1 million of these and train it as 1, 0. If the similar problem like this in Calabi-Yau manifolds or in group theory would have trained instantly to over 90%. But this, you could not break the 50%, yes, let's guess, and the chi-square is 0.001 or something, and you just could not do better than randomly guess. I tried every single neural network I could get my hands on, because I don't know which one to even choose a priori, right? Because how would I know? You read in the literature, recurrence networks are good for time series prediction. We tried this one on primes, 0, which is good in a sense. I'm sure people have tried this. Because but they might be less public about it because they would try to break a bank. But
Okay, let's thank Yang-Hui.